we're going to cover section 4.2, logarithmic functions. The quiz on Monday really is one section. It's because remember 31, 32, and part of that little handout I gave you in class 33 was just working on the graphs of those rational functions. So it's rational functions, and then there were a couple of problems on the handout I gave you for class 33. Remember, there was no lecture. It was the catch-up day where you just had 3 or 4 problems to work on. First one started, the first new problem was like a parabola where you had to find the value for A. So it's really not a lot. Most of you have done all of the major work for rational functions already, so you shouldn't have to worry too much about it over the break. Just maybe Sunday night review it, and or sometime Sunday you should be fine. And have a great break, everybody. I hope you get a little bit of rest for the last couple weeks of class and all your other classes, and you'll be fine, I hope. All right, so I asked you to match these 4 functions with their graphs, and I've checked everybody's paper except for Shane's and Kate's, but why don't we just fill this in with what was the graph for number 1? All right, it was b, y equals 2 e to the x, because we saw that we took our original function, e to the x, and we doubled all our y values, which is this function, because the 2 is on the outside. And what was number 2? D. And very similarly, all our y values, e to the x, were multiplied by 1/2 or divided by 2. And that's this function here. And again, you look at your key point here, 0, 1. Here it went up to 0, 2, and here it's gone down to 0, 1/2. And then we can see that this black function here has been shifted over from our original parent function, e to the x. How many spots? Again, go to 0, 1, 1, 2 to the left. So that means we're looking at this function right here, a. Okay, x plus 2 means you've shifted to the left 2. And then by process of elimination, the only one you have left is your vertical shift down of c. Okay. So we're going to start logarithmic functions today. And before we start logarithmic functions, let's go over each of the 5 major ideas of inverse functions. Now, inverse functions may seem like a lifetime ago. Must probably, 3 or 4 weeks ago, right? We did inverse functions. So Cameron, why don't we just go right around, and Cameron, start us off with A. So we'll just review some of the major points about inverse functions. Okay. Adam, B. Okay. C. Kate. Right. And f to the -1, how else can we read f to the -1? F inverse, okay? So the domain of f inverse, the domain of f is the range of f inverse, and the range of f is the domain of f inverse. Okay? And D, Glenn?
The graph of f to the 1 is the reflection of the line about the line y equals x. That is to get points on the graph of f1 first coordinates of the graph of f.
So if we have the graph of f, and we know that these 2 points are on the graph of f, then what's the points look like on the graph of f inverse? Yx. We just reverse them. Whatever the input is in your first function f, and whatever the output is, it just completely reverses in f inverse. Your output is now your input, and your output is the original input of your f function. Okay, so they just swap places. And then the last one was really an important property, and it's part of the definition of inverse functions, is that when you compose these 2 functions, you get right back to where you started. They undo each other. Okay, that's a very important idea. no matter which order you compose your functions, you come right back to your original input x. Yeah, I used to refer to that as the round trip, right? No matter you go, it's like going in a circle. You come right back to where you started. Okay, so let's take a look at, again, we talked about these two functions on Monday. We talked about their domain and their range and the key points they went through. And again, remember, you can always get the value of your base for your exponential function by noticing, first of all, you know if it's in this form, f of x equals b to the x. You know it's in that form if 0, 1 is on your graph. It has to pass through 0, 1 to be a function that looks like this. And then to find the value of b, you look at the coordinate that goes along with 1. Because think of it, if you put a 1 in here for b, f of x equals b to the 1, whatever your y value is the value for b. So look, 1, 2. So 2 equals b to the 1, b's got to be 2. So these points, when you have a function that's f of x equals b to the x, 0, 1, and 1b are your key points. So again, you look at this function, you see you got 0, 1, so you automatically know this has the form f of x equals b to the x. And then to find the value for b, you look right here, and it's 1, 1/2. So we know this is the function 1/2 to the x. Okay. We talked about horizontal line test on Monday, that these were both 1-to-1. They were reflections across the y-axis of each other. Okay, and because they're 1-to-1, we know they have an inverse function. So let's plot the inverse function of f of x equals 2 to the x. Let's do it by hand because we know how to do that. And then we'll take a look at the notation for how to write the inverse of an exponential. So here's our doubling function, f of x equals 2 to the x. So let's find some key points on this function, and then we'll just swap the input and the output. So let's see, if I was at -1 right here, what would be my value at -1? What would be my output? 1/2. Now, how did I get that? Well, if I put -1 into my function is 2 to the -1. So I get 1/2 because that's equal to 2 to the -1. Okay? So my point on this graph is -1, 2 to the -1. And I'm keeping it in exponent form, and you'll see why in a minute. Okay, and we know at 0, we go through y equals 1, and that's the same as 2 to the 0 power. So we've got 0, 2 to the 0 for our point. So here's our x and our f of x value. Okay. At 1, let's see, at 1, we know that's another key point because it tells us the value of our base. So our base is 2, which is 2 to the 1. So at 1, I'm 2 to the 1. At 2, I'm 4, which is 2 square. And at 3, I'm 8, which is 2 to the 3rd. And at 3, I'm 8. And we can just keep going on and on like this forever and ever in both directions. There's no restriction because our domain is all real numbers. And in fact, if we put in -2 back here, I'm at 1/4, which is 2 to the -2. So at -2, I'm 2 to the -2. Okay, so I really have enough information to actually start plotting my inverse function because my inverse function reflects about the line y equals x, which is just your linear line, slope 1. So all you do, I got to use a different color. Let's do that. Boom, boom, boom. Go like this. We'll put our line y equals x in. I'll try, all right, connect it. Okay. So there's the line y equals x. Okay, and now I just reflect these individual points right across the line y equals x. So 0, 1 now becomes what? 1, 0. 1, 2 now becomes 2, 1. 2, 4 now becomes 4, 2. 3, 8 now becomes 8, 3. If I kept going, 4, 16 would now become 16, 4. Okay, now let's go the other way. Negative 1, 1/2 now becomes 1/2, negative 1. Negative 2, 1/4 now becomes 1/4, negative 2. I think I can get in there without looking like it's on the y-axis. Okay, so with my exponential function, as x went out to negative infinity, this graph got closer and closer to the x-axis. And now with my inverse function, as x approaches 0, what does the value of my function approach? What's it getting closer and closer to? What line am I getting closer and closer? 1/2, 1/4, 1/8, 1/16, 1/32. What number am I getting closer and closer to? Y equals 0, right? Yep. Any number except for 0 raised to the 0 power is 1. Yep. So that's what my inverse function looks like. So as x gets closer and closer to 0, my function gets closer to 0. That's your vertical asymptote. As x goes to positive infinity, my function also goes to infinity. It continues to grow. It's a very slow growth. That's one of the properties of a logarithmic function. So if we were looking at modeling a situation, like trying to do a regression, and you notice something that increased and then fairly quickly, but then the growth over time, say, was really, really slow, a logarithmic function would be a good model for that. Versus your exponential, where things grow very rapidly. Look at your exponential's real slow. Oh my God, way out here. And then once you start hitting your positive integers, your positive real numbers, you grow very quickly. Okay. And the same is true here. Your growth here, but then look at how slow it becomes. It almost looks like it's a horizontal line, but it's growing at a much slower rate. All right, so this is what the graph of your inverse function looks like for your exponential. Okay. So what else do we want to talk about? Ooh, so what are the key points on your exponential? Well, on your logarithmic function. So on our exponential function, it looked like this, which is 1, 2 in this case. So now when we go to the inverse, we want to make sure that 1, 0 is on that function, because then we'll know it's just, I can't tell you the name of the function yet. And then you look here, you look to see what value of x will give you a 1, and that's going to tell you your base. So if you go here to your function and you look at y equals 1 right here, you notice that you're at 1, 2. So that's what your base is. It's your original base. So let's over here write our inverse function. Even though we don't know the name of it yet, we can still play the same game. If we take our output for our exponential function, like 2, and we put it into our inverse function, what do we have to come back to? Okay, our original point was 1, 2, right? 1, 2. And when we reversed it, we were at 2, 1, right? So we're at 2, 1. I'm just going to write that, oops, over here, 2, 1. Where's my eraser? Here's my eraser. Okay. 2, 1. I didn't write that right. Sorry, folks. This is, no, I did that right. 2. All right. When I'm at, so I'm switching my inputs and my outputs. So what would this point 2, 4 become on my inverse function? We graphed it. Go ahead, Glenn. What? 4, 2. Okay. And my 0.38 on my exponential function became 8, 3. Okay. And now let's go the other direction. Well, we'll go to 0. 0, 1 now became 1, 0. So we now have an x-intercept, which we didn't have. Notice we have no x-intercepts on our exponential function. We had a y-intercept. Now we have an x-intercept and no y-intercept. Okay, and then at negative 1, 2, we reverse that. We have 2, negative 1. And then at negative 2, wait a minute. Guys aren't watching me. I'm not watching myself. It's 1/2. Negative 1, 1/2 becomes 1/2 negative 1. And then negative 2, 1/4 becomes 1/4 negative 2. Okay. Whew, that's a lot of work, but you see that as this one increases this way to infinity, this one is decreasing to negative infinity. As this approaches the x-intercept, this is now approaching the y-intercept. So it makes sense for all that we've learned, but we still don't know the name of this thing, right? We don't know the name of it. So let's see if we can come up with the F inverse function. Well, let's go through the steps we went through at the beginning of our inverse function lecture. So let's see if we can remember what those steps were. We write our function down, and then we have to undo everything that happened. Yeah, I know. Right, so remember our first step was we write f of x as a y. That was our first step. And then we interchanged x and y, and we solved for y. That's how we found our inverses. So let's try it. Let's see. Now solve for y. How are we going to get y downstairs? Someone in my first class said, why don't you take the y-th root of each side? We ended up trying that, but we ended up trying a couple of things and kind of got nowhere. All right. So all of the algebraic methods that you've learned to date, and we've learned quite a few, won't solve this equation for you. Darn it. All right. Nothing that you've learned so far. Now, you may have seen this in previous classes, like maybe in high school, for those of you who are recently out of high school. But nothing that we've learned to date is going to help us solve this equation. So you see this little phrase here? Just go with me here. I'm going to tell you the notation that we use for F inverse, what we call it, and then we'll see how to use it. The notation, the thing that undoes 2 to the y is log base 2 of y. This is what we call our inverse function. This is the inverse function for our exponential function. It's called a log function. Okay, so we write it this way. This is the inverse for this exponential function. So f of x equals 2 to the x, we call the exponential function. Its inverse, we write this way, is called a logarithmic function. I'm just going to put log period instead of writing it all out, logarithmic. All right, so let's figure out what this logarithmic function looks like. Well, we actually saw what it looked like. Here it is right here. Here's log base 2 of x. This is what it looks like. Let's figure out how we put numbers in and get numbers out. Well, you actually already did that too. You did it over here. You put some numbers in and you got some numbers out. But I want to kind of show you an interesting way of finding that. So let me just take a picture of this for a second. let's take this input-output table, and I'm going to cut and paste it over here. Cut and get a new page. Let's paste it. And I just want you to see a little different form of this. Did you have a question, Adam? It does. No, because what does a square root function look like? The square root function for the positive square root starts right here, right? Okay, first of all, we don't, on the log function, we can never have x equals 0. And this has no vertical asymptote. Okay, so the only similarity is sort of this part of the shape right here. Yep. And the fact that as x goes to infinity, it goes to infinity as well. The end behavior is similar. But what would be really interesting to do real quick, I think we have a minute here. Let's go to GeoGebra and let's put the two graphs together so we can take a look. So, no, it would be 2 squared. It would have to be, right? You're looking at the square root function is x to the 1/2. Now we're looking at 2 to the x. So remember, your variable is now your exponent. Okay, so let's take a look at that. So let's call f of x, x to the 1/2. This is our square root function. Okay, and now let's look at an exponential function like 2 to the x. That's exponential. And now let's take, I've never tried a log function. Let's see. What if we just put in log? Let's try it. H of x equals, let's see what happens when I put log in. Oh, good. Log normal. Oh, no. Logistic. I don't want any of that. How do I put in, I've never graphed a log function on GeoGebra. Let's see. Where's my commands? If I can't find it real quick, I'll have to look for it over break. Let's see. You see log normal, that's statistics. How you graph the log function? Ooh. Inverse normal, inverse gamma, no? I'll have to check that out. Wonder how you graph a log function. Wonder if you could put G inverse in or anything like that. Let's try that. G, this is just a guess, folks. I don't know if this will work, if it recognizes that notation. Yeah, that's, I wonder what that gave me. It's definitely, yeah, let's change that. Let's just take out the x. Oh, so that's how you do it. No, they don't show the vertical asymptote. No, what the heck did it do? Oh, they did 2 to the negative x, so they did 1/2. So, well, first of all, we don't need any of these in here because we're not doing exponential. We're trying to do the log functions. And so what I would do next is I would go to my help button and I would ask how to graph a logarithmic function. I know, but now I'm curious. I hate this. I know. This is like why people become math teachers or math people, because they can't let things go, right? We're obsessive. Nope. It's not square root is comparable to squaring. It's the inverse of a polynomial function. It's not the inverse of exponential. X squared is a power function. It's a polynomial. 2 to the x is exponential. What did it say? Oh yeah, great. All right. Well, I'll have to play with that over Thanksgiving. I won't have my computer with me, but hopefully someone will have a computer. I know I can't relax either until we find out. Okay. So what I want to do, folks, is I want to play a little game with you. I want to write these as 2 to a power instead of, we simplified each of these. So 1/4, remember, was 2 to the negative 2, and the answer was negative 2. That's the point we plotted. 1/2 was 2 to the negative 1, and that's was its partner negative 1. And 1, 0 is 2 to the 0, 1. And, excuse me, 0. And 2 is 2 to the 1, which is 1. And 4 is 2 squared, and 2 was our output, and 2 cubed, and 3 was up. So these are the points that we plotted. These are the points that we plotted for F inverse of X before we knew it was called log, all right? So just take a look down this column, and then take a look down this column and see if you notice anything. Do you notice a pattern? Do you see how you might be able to go from your input directly to your output? This first column is your X values on this function right here, right? We had 1, 0, we had 1, 2, we had 2, 4. So all I did was I put them, instead of calling them 1/4, 1/2, 1, 2, and 4, I just put them in exponent form, right? That's all I did is I took these inputs, which were the outputs of your exponent function, I just put them in exponent form right here. So do you see any relationship going from your input to your output? Right, because I chose that increment to increase by 1 along my scale because it was easy to do, but I don't have to. I could have put in 2 to a power that would give me 1/2, which would be a little tricky, but yeah, the exponents, look, are the same as your y values. Isn't that what's supposed to happen with inverse functions? Let's see. F of x is 2 to the x. You put in 3, what do you get out? 8, but let's not call it 8. Let's call it 2 to the third. When I go to my inverse function, I put in 2 to the third, 8. I come back to 3. I'm at 2. I get 4. I put 4 into my inverse function. I come back to 2. I put 0 into my exponential function. I get 2 to the 0 or 1. I put 2 to the 0 in. I come back to 0. Okay? So whatever the exponent is on your input, this is your input into your inverse function. The answer is the exponent, because you've got to come back to where you started. That's how inverse functions work. So you basically, whatever you put into your inverse function, which we are now going to call our log function. So this is called log base 2 of x. So let's write this now, what it looks like. F inverse of x. What am I putting in? I'm putting in 2 to the third. What's my answer? When I put 2 to the third into my log function, my answer is 3. I lift off my exponent. Here's F inverse, log base 2. What do I put in? 2 squared. My answer is 2. I lift off my exponent. Log base 2 of 2 to the 0. My answer is 0. I lift off my exponent. All you're doing is saying, what number do I raise 2 to? It almost sounds ridiculous. What exponent do I raise 2 to get this, 2 squared? The answer's looking at you right there. I raised 2 to the second power. So you're just switching places with your input and your output. So again, saying it a little slower, your exponential function is right here. What do you put in? A bunch of real numbers, right? Those real numbers are your powers. The answer, 2 to that power, becomes the input into your log function. The answer the output of your log function has to be your original exponents. So all a log is an exponent. That's all it is. So you can write them as equivalent statements. If you have this statement, you say this is in exponential form. This is what you're used to seeing, a little bit more anyway. To put it in log form, to take that equation and make it into an equivalent equation, you say, well, my log must have the same exact base as my exponential. Here's my base, b. So I say what base I'm working with. The result, the output of my log function has to be the exponent. What's the exponent here? What's the exponent? Y. So that's got to be my answer. And the output of my exponential function has to be my input for my log function. So these two equations are exactly the same. They're exactly the same. They're inverse functions of each other. So this is logarithmic form. Now we're going to spend a good 10 minutes just going back and forth. So if it feels a little fuzzy, it should feel fuzzy. Excuse me. Almost. Excuse me. Okay. Stare into the light. So our directions here are write each equation in its equivalent exponential form. So here's log form. We want to write this as an exponential equation, not a logarithmic equation. So you look at your log and you see what is its base. Where's the base on this log? It's a little subscript right there. That's the base. So that becomes the base of your exponential function. Okay? The answer to the log is an exponent. It's just the power. So here's your power or exponent, right? That you raise 3 to. So I raised 3 to the second, and now I'm right back to 9, which is my input. So if you were playing a little game on a graph, if you started with your exponential function, your exponential function would be 3 to the x. That would be your exponential function. And if you put 2 in, your output would be 9, or 2 comma 3 square. Now in your log function, log base 3 of x, that's your inverse function, your log function, you put in the output, and what you come back to is your round trip. You come right back to your original exponent. It just identifies the exponent that was on your original exponential function with the same base, base 3. Your output and input swap places. Let's take a look at this one. We get a -1 for an answer. And so we want to write this as an exponential form. You got to identify your base. Shane, can you tell me what the base is? 8. It's the same as the base on the log. Now, what exponent do I raise 8 to? Well, how do I figure out which one of these is the exponent? Remember, the answer to your log function is your original exponent on your exponential. And we know 8 to the -1 just means 1 over 8 to the first, which we write as 1/8. So that's moving from log form into exponential form. And now let's try it the other way. Let's go from exponential form into log form. So let's write this as an equivalent logarithmic equation. Okay, so someone want to help me with this? I know I start with the word log on both of these. Okay, and what goes where? Two is the base, okay? So do I put it here? You mean as my input? Okay, 8. Yep, I put a 3. The input on my exponential function becomes the answer to my log function. The out, it doesn't matter which side it's on. It's okay. Either way, Ricky's fine. And then the output of your exponential is the input of your log. Now look at if we just wrote it this way. You can see the liftoff idea. Write 8 as 2 to a power. How can I rewrite 8? 2 to the what? 2 to the third. Look, your bases are the same here. Just lift off your exponent. Boom, you're done. So if you can write your input as your base to a power, you just lift the power off. That's all you do. All right, so how about this one? Log, what's my base going to be? 6, because my base here is 6. The base of my exponential is 6. Okay. The answer to my exponential, my output becomes my input. And my input to my exponential becomes my output. Written another way, if you write 136 like this, 1 over 6 squared, which is the same as 6 to the negative 2, your bases are the same, just lift off your exponent. So let me give you another one. You'd figure this one out at your seats. See if you can figure that one out at your seats. -2, right? And how do you check? This is a neat thing you can always check. You check your logarithmic equation with an exponential. So you say, I keep my same base. I raise 8 to the -2, and I better get my input for my log function. And I do. 1 over 8 squared is 164. Okay. All right. So let's take a look at these. Log base 10 of 100. Again, write 100 as 10 to a power, and then just lift the power off. So how do I write 100 as 10 to a power? No, not 10 to the 10th. 10 squared. Now let's lift off the power. 2. So log base 10 of 100 is 2. I check it. I keep my base the same. I take my answer. It becomes my exponent. And the answer to my exponential, the output, is my input of my log function. Okay, log base 5 of 1 over 25. I want to write 1 over 25 as 5 to some power. What power would that have to be? -3, right? So log base 5 of 5 to the -3. My answer is just to lift off my exponent. Again, I check it. 5 to the -3 equals 1 over 5 cubed, which equals 1 over 125. It checks with my input into my log function. I'm golden. I'm going to let you all think about the next one. You may even have to do some cross-table pollination to figure this one out, which is okay. So what do we get for this answer? A half, right? Because the base is 36. When I raise it to the 1/2 power, it says take the positive square root of 36, and my answer is 6. Huh? How does what work? What do you mean? You just told me my answer was a half, right? Oh, because you want to say, if you write 6, if you rewrite 6 like we did over here, like what exponent would we raise each of the bases to? So if you do this, you say log of 36 is 36 to what power? Just like we did here, we said, what do I have to raise this base number to get 1 over 25? You said -3. What do I have to raise 10 to get 100? It was 2. So what do I have to do to 36 to get 6? I have to take the square root, and the square root we write as 1/2 power. Okay? All right. All right, so now we're going to look at some basic log properties. basic log properties. So again, if we just put the power right there, what's our answer? Log B of B. What's the power? Lift off the power, Shane. What's the power on B? No, it's getting raised to the first power. This is what's the input. The input is B. Its exponent, the exponent of B is 1. Okay. And you check it by saying B to the exponent. The answer of the log has got to bring you right back to what you input. Okay. Now, if it had said log base B of B to the B, right? That's what you were thinking, right, Shane? If it looked like this, right? You'd have to have 3 B's in there, though, right? Then your answer would be B. You see the difference? Okay, because this was just a B. All right, now here's your favorite, Shane. Log base B of 1. How can you rewrite that so it's B to a power? How can you rewrite 1 so it's B to a power? B to what power gives me 1? Yeah, your favorite, right? Log base B of B to the 0. So you lift off your exponent, you get 0. Notice people, what point this would be. What points would this be, no pun intended, on your log function? This is the point 1, 0. That's your x-intercept. Notice it's directly reflected across the y equals x line from 0, 1. What's this point? B, comma 1. So it's the points that we looked at a few minutes ago when we did our graph. Where is that graph? Where are you? Way at the beginning. Trying to find it. Is it this one? Yeah. Nope, it's not that one. Keep going. Here we go. So remember, on the original graph, we had 0, 1, and then we became 1, 0. We had 1, 2, we became 2, 1. So those are key properties of exponents, of logs. Log base B of B is 1 because it's the point B1. Log base B of 1 is 0 because 1, 0 is a reflection of 0, 1. Now, to do these next properties, they really mess with your mind a little bit. So let's review something for a minute. Let's review composition of inverse functions. Okay, I don't want you to look at them yet because they look a little scary, but they're really easy to evaluate once you see what's going on. So we just said that one of the properties of of inverse functions is that their composition, no matter which order you do the composition in, brings you back to your original value, x, your original input. Remember, we called this function the inside function. And then the outer one is the outside function. Okay. So let's take a look first at f inverse of f of x equal to x. Let's just go back and play with two functions real quickly that we know are inverses of each other. Let f of x be x plus 3. What would be the inverse of x plus 3? How do you undo adding 3, folks? You subtract 3. Thank you. So I'm going to put f of x as my inverse function, f of x into my inverse function. So let's do that. So my inverse function looks like this. I'm going to put f of x in. So I put x plus 3 into where I see x in my inverse function, subtract 3, and I'm right back to where I started. Now let's reverse the order of the composition. I'm going to do f of f inverse of x. So f of x is x plus 3. I'm going to input my inverse function where I see x, add 3. I'm right back to x. Now let's do this same thing, but with these two functions. F of x equals, let's stick with our 2 to the x. And its inverse function is log base 2 of x. All right. So in each one of these spots, this is your input. Where you see x is your input. All right. So suppose I want to do this one first. F of x is my inside function, and I want to compose it with the inverse function. What should be my answer when I compose those two functions? X. Okay, because they're inverses. So put f of x where you see x in your log function. So your log function looks like this. I'm going to put f of x in where I see x. So now I substitute f of x. F of x is 2 to the x. I lift off my exponent. I'm back to x. Cool. You kind of get that from what we just did. You know, you kind of get that. We've played with that. It's the next composition that your mind goes, what? When you look at it. But it works the same way. You're composing now your inverse function. You're putting your inverse function as input into your exponential function. So your exponential function looks like this. So you're going to put that entire inverse function in as its exponent, and it looks really like funky. Your answer is just x. Come right back to where you started. Trying to reason this almost sounds like you're going in a circular sort of, if you try to reason it, you say to yourself, this thing represents the power you have to raise 2 to get x. So you take that power you have to raise 2 to get x, and then you raise 2 to that power. You got to come back to x. It almost sounds silly. Right? This thing right here, you've got to be able to say it. Really, all you have to do is recognize that it's the composition of your inverse functions, because your answer is always going to be x on both of these. But if you try to reason it out, you first say to this, what does that mean, the thing in the green box? The thing in the green box is an exponent. That's all it is. What exponent is it? It's the exponent I attached to 2 to bring me back to x. So if that's what the green box is, the exponent I applied to 2, I'm going to put it in. There's my exponent I applied to 2. Where's it going to bring me? Back to x. So my answer is x. It's a little harder to understand and see. So what might be good is if you try something that we can see the answer for. So let's do this. 10 log 10 of 100. It's sort of easier when you actually see it with numbers. So what's the answer to this? I'm even going to cover that. Log base 10 of 100. What's my answer? 2. Because this is asking me, what power do I raise 10 to get 100? The answer is 2. Now look what I'm going to do. I'm going to apply that power to 10. Where am I going to be? Right back to 100, which is your input right there. Huh? I have no idea. I've never tried it. Okay, so we'll find out if you have to do it. Okay. I'm sure they've got instructions. So these two properties right here, when you look at them, I want you to see, I want you to see your exponential function. So if you cover this up, you see your exponential function. Your exponential function is being put into your log function. That's the composition of inverse functions. You have to come back with your original input. Here, see b to some power. That's your exponential function. Your inside function, what you're putting into b to some power, is your inverse function, your log function. Those undo each other, so you're back to x. It's a lot of explanation, but once you actually play with these and recognize them, then you'll get into the habit of just saying, oh, my answer is just x, whatever x is in both of these cases, because you're composing inverse functions. All right, so let's play with this a little bit. Before we play, I just want to note, if you take out your calculator, and if you don't have your calculator, just sort of look up here on mine. You only have 2 log buttons on your calculator. You have log right here, and you have ln. If you look directly above each one of these, you see the exponential function that it's the inverse of. So log is the inverse function for 10 to the x. So log must have 10 as its base. When you see log base 10 of x, it's so common, so commonly used to have base 10, they don't even bother writing in the base. So when you see a log without a base written on it, it's understood to be 10. So if you see something like this, log of 10,000, the base is understood, even though they don't write it, to be base 10. So your answer here is 4, because 10 to the 4th is 10,000. Okay. Similarly, if you recall when we did e to the x in Monday's lecture, we said anything e was what was called the natural exponential function. E to the x was the natural exponential function. So when you have log base e, it's called the natural log. So they use this notation right here, ln, to represent natural log, which means your base is e. Okay. So notice here you have your ln button, and if you look directly above it, there's the inverse function e to the x, the exponential, natural exponential function. So if you see log with no base, you know it's base 10, and if you see ln, you know it's base e. So let's take a look. So here's our first log, log of 1,000. These you could actually throw into your calculator and actually get an answer if you wanted to, but I think you can do this first one without looking at your calculator by just saying 10 to what power is going to give me 1,000? 3. Just count your zeros. 1, 2, 3. Okay. Now this one is a fraction, so you know your answer's got to be a negative number. It's log of 1/100th, which you can write as log of 10 to the negative 2. So my answer, I lift off my exponent, is negative 2. Notice this, folks. If I put the baby e in here as the base, I'm composing. This is an example of when you compose e to the third with the natural log. I'm putting e to the third into its inverse, the natural log function. So what do I get for my answer? My bases are the same. My answer is 3. You lift off the exponent. The next one I rewrite. I write it as e to the negative 2. My bases are the same. How do I know my base is the same? Because I know when I write that ln, it's really like the log of a little e there. So my bases are the same. I lift off my exponent. Natural log of 5. E to what power gives you 5? If you know that off the top of your head, you're a savant. Okay, I don't know. So let's see. This is where we have to use our calculator. We say natural log, because we only have 2 logs we can do right now anyway on our calculator. Let's clear everything. Oh, clear. All right, I know. Natural log of 5 is 1.609437912. I'll probably tell you to estimate it to two places, so 1.61. Okay, but if you wanted to check this, what button would you use to check it? To check the natural log function, what would you use to check it? Okay, because we got e to what power gives me 5. So this is how you check it, right? Here's your answer. We're saying e to the 1.609437912, and this goes on forever, is equal to 5. So we say e, you check the natural log by using its inverse, and you want to put that whole number in, because if you put in any kind of estimation, you're not going to get exactly 5. So how do I put that whole number in without having to write it all over again? And second answer, right? You want to use your second answer button and hit enter, and there's your 5 back. So you've done a round trip. You know you're right. Okay. Yeah, it's you don't even write it in, Shane, because it's understood when you write When you write this, it's understood to mean this, log base e. So when you write ln, think of natural log. Natural exponential is when you have e as your base, so it's log base e. Okay. All right, so let's take a look at the graphs again of the log function, log base 2 of x, and its inverse 2 to the x. And let's make some notation about various properties that it has. So we'll just focus on this first one here, where we have b greater than 0, bases with b greater than 0. The blue is our exponential, the red is our logarithmic. So what's the domain? So we're looking at the domain of our log function here. So we're looking at the domain of log base b of x. So just focus on your red function. Where would you start and where would you end? How would you represent the domain? Either in words or in interval notation. What would your domain be? Okay, and then what do I, oh, both in parentheses, Kate? Yeah, thank you. Because what's the range of your blue function? Everything above the x-axis, right? All positive real numbers. And that's how we write it in notation, interval notation, or you could say all positive real numbers. We're looking at the domain of the red one. But remember what I said, Ricky, that why I went back to the blue one, because the domain of the red one is the range of your blue one. Okay. Yeah. So the range of my red function, my log function, will be the what? Domain of my blue function. And what's the domain of your exponential function? Right, negative infinity to positive infinity, or all real numbers. Right, all real numbers. Okay, is my logarithmic function 1 to 1? Yep, better be, because we just looked at its inverse. Yeah, it passes the horizontal line test. Horizontal line test passes. Does my red function have any turning points? The first red function. Does it have any turning points? No, it just keeps, it's always increasing. No turning points. Does my red function have a y-intercept? No, because x can never be 0, because 0 is not part of the domain. So absolutely no. You can never take the log of any base of 0. Log base b of 0 is not defined. Because you can't get 0 as an output for your exponential, so it certainly couldn't be an input. You can't take the log of a negative number either. If I tried doing this to you on a test, log base b of a negative number, like any negative number, -7, you say, no can do. Don't try to fool me, Linda. I can't take the log of 0 or negative numbers because it's not in the domain. Okay, x-intercept is 1, 0. Do I have any asymptotes with my log function? X equals 0, and that's the equation for what part of my graph, x equals 0? The y-axis, right? So I have, for my first red function here, I have the negative part of my y-axis as the vertical asymptote. Okay, and the end behavior as x goes to positive infinity, right? This thing approaches infinity. Very slowly it grows to positive, and we don't talk about x going to negative infinity because that's not part of our domain. Okay. Then you can play the same game with this function. This is your decay function, and this is what the inverse looks like if you do the same thing we did originally. Take some points on this original function, b to the x, and then you swap the input and output. Now, some people can look at this blue function and do that reflection and see this. Other people have to do point by point. I'm one of those people. I can't like look at this and see how it automatically becomes this red one. But some people have that incredible visual talent to do that. It's not one of my talents. So this is what the inverse of a decay function looks like. But notice all of these answers are very similar except for the asymptote. The asymptote still is your y-axis, but it's the positive part of your y-axis. Just like with your decay function, you had the x-intercept as your horizontal asymptote, but it was the positive part, not the negative part. Did I say asymptote before, or did I say axis over here? Anyway, you still have an asymptote that's your y-axis. It's just the upper, your positive y-axis, versus this being your negative y-axis. All right, so let's do the same game we did before with looking at our log function. If I asked you, if I didn't tell you, I want to ask you this question. If I didn't tell you that this was the graph, because this happens on finals a lot, I give you a graph like this and I say, find the equation for that function. Notice I've given it to you right here. I've told you that it was log base 2 of x. But if I didn't tell you that equation, where do you go to look to see what base it is? How do you know what base this logarithm is? What's the point that tells you that? 1, 0 tells me something. 1, 0 tells me that I'm looking at a log base b of x, and I'm not doing anything to the outside of it. I'm not trying to stretch it or shrink it. That's what that 1, 0 tells me. But I'm trying to get at how do I find the base? What point on your exponential function told you what the base was? What was the key point on your exponential? 0, 1. What would be the point on your exponential that would bring you back to 2? Your exponential would have 2, would be base 2. What brings you back to 2? What power brings you back to 2? 2 to the what power? 1. So 1, 2, right? When you're 1, you get 2 out of there. That tells you what your base is. So how's it going to be reversed? 1 now is not going to be your input. It's going to be your output on your log. So you now want to look at where your log function hits the horizontal line of 1, y equals 1. So you just come right across like this. That's your output, 1. So whatever the input in is has to be your base. So come right down, and there you go at 2. So the point 2, 1 is the point that tells you the base of your log. So when you look at any log function, if you know, as Adam says, if you know 1, 0 is on that function, that's the first part. If 1, 0 is on that function, then you draw a horizontal line across at y equals 1 and find the x, the input value. That input value is your base. All right, so let's go down and see how this thing gets transformed. And let's see if we can come up with the equation of the transformation. So, actually, I'm going to give you the transformation, and you just got to graph it. Okay, so what's happening? Can we describe what's happening in this first function to log base 2 of x? How are we transforming it? Are we working on the input, or are we affecting the output? What's being affected here? Input or output? The input, because x has been changed. It's not log base 2 of x, it's log base 2 of the expression x plus 3, or the quantity x plus 3. Okay, so how am I shifting now if I'm on the inside of my function? Oh, you already told me. Horizontally, it's a horizontal shift to the left 3. Okay, so I literally just take that graph, I pick it up, keep the shape exactly the same, but move it 3 places to the left, 3 units to the left. So what's going to become my vertical asymptote now? Not x equals 0 anymore, but what? x equals -3, right? So I put a vertical line straight down here like this, okay? And now I know how to act when I get close to that vertical line, and I just take a couple of points. 1, 0, which was the first point Adam identified. I shift it to the left 3, becomes -2, 0. My 2, 1 now becomes -1, 1. My 4, 2 now becomes, oh, I'm going to the left 3, 4, 2, what was originally 4, 2 now becomes 1, 2. And I don't really need to do anything after that because I know as I get closer and closer to -3, I hug that down to -infinity, and then I just keep the shape the same. There we go. So that's how I would graph that transformation. What's the next one going to do? What verbally describe the transformation? Verbally. What's happening? What kind of transformation when I put the negative on the outside? Am I affecting the x values or the y values, the input or the output? Yeah? The y values, the output. So all my outputs are going to change to their opposite. Right. So 1, 0, what's going to happen to 1, 0? 1, 0, I change my output to its opposite. 1, 0, it stays the same. Okay, 4, 2 becomes what? 4, -2. I just changed my output. So let's see, 4, -2 is right here. 8, 3 becomes 8, -3. Let's try some of the ones as we're getting closer to 0. When x is 1/2, excuse me, when x is -1, we were 1/2. So what are we now when we're -1? What are we now? Is that right? Doing this right? Can I have a -1 for my log as an input? No. So what's the number that goes in there? Folks, look, here's your x. Here's your log base 2 of x, and just change the sign. So look at your points here. You had 1, 0. When you change the sign of 0, it stays the same. You had 4, 2. When you input 4, your output is 2. Now it's -2. When you put 8 in, 2 to the third is 8. So the answer is 3. You change the sign. So what if I do, what could be some other input now? I can only be a number between 0 and 1. So what might be another input? How about 1/4? 2 to what power gives me 1/4? -2. I change my sign, I become +2. So at 1/4, I'm up here at 2. And at 1/8, I'm up here as what? If I go 1/8, what would be my value? 3. I just change it, right? So 1/8, I'm up here at 3. I'm a little closer to my y-axis. So this function looks like this if I reflect it over the x-axis. So that's it. I think I had one more question, but I kept you 3 minutes late. I'm sorry for keeping you 3 minutes late. Have a great vacation. Get lots of rest. Have some fun. Relax. If you eat too much turkey, make sure you're someplace where you can take a nap. So what's the name of the chemical in turkey? Yeah, that's right.